Hello and welcome to our presentation. I'm Jiacheng Zhang from Purdue University. Today I'd like to talk about the numerical uncertainty in the density estimation for background-oriented Schlieren measurement. BOS is an image-based density measurement technique based on the apparent distortion of a target pattern viewed through a medium with varied density. The measurement chain of BOS includes the optical imaging and the displacement estimation of the dot pattern, from which the density gradients are determined. Cross-correlation is a common approach to estimate the displacement from the images. The density fields are then obtained by the spatial integration of the density gradients with finite-difference method. In BOS, the density gradient integration is normally performed by solving the Poisson equation, which is also the method focused in this study. The uncertainty quantification method introduced in our previous study considered the uncertainty sources from cross-correlation and propagation through the integration process, as demonstrated in the schematics below. In addition to the cross-correlation process, the finite-difference integration of the density gradients can introduce systematic error, which was not considered in the previous UQ analysis. As shown in the fields of the random error and the bias error from our previous UQ analysis below, it was found that there was significant bias error in the obtained density field. This bias error was not captured by the previous UQ method, which focuses on the random uncertainty from the cross-correlation process. The objective of this study is to investigate the source of the bias error and estimate the numerical uncertainty during the finite difference integration of the density gradients. First, we propose to use the Richardson extrapolation to estimate the numerical uncertainty from the finite difference integration of the density gradients. The Richardson extrapolation was mainly used in CFD simulations to estimate the numerical error in order to achieve better numerical accuracy. The Richardson extrapolation method assumes that the bias error was due to the truncation error from the finite difference integration, which depends on the order of the numerical scheme and the grid spacing. By evaluating the residuals between the solutions obtained from different grid resolutions, the bias errors can be estimated as expressed by the equation. The term epsilon h suggests the truncation error from the grid spacing h. F means the solution obtained from the grid spacing h. R is a downsampling factor that describes the difference between the fine and the coarse grids. P is the order of accuracy of the numerical scheme. For the Richardson extrapolation-based error estimation to be accurate, the solutions from all grid spacing levels need to be smooth and within the asymptotically convergent range. However, these requirements can be difficult to satisfy even for CFD simulations. Therefore, the Richardson extrapolation is more commonly used to estimate the numerical uncertainty instead of the numerical error as expressed in the equation, where U is the uncertainty indicating the 95% confidence interval, and Fs is the factor of safety, which was empirically chosen. It should be noted that the Richardson extrapolation method proposed for CFD simulations may not be applicable to experimental BOS due to the more severe limitation in the spatial resolution, as many steps require downsampling the measurement, which may be insufficiently resolved. Therefore, we have proposed several adaptations to use the Richardson extrapolation on experimental BOS to estimate the numerical uncertainty. First, we will use the formal order of the numerical scheme as the order of accuracy. Second, we will use a factor of safety of 1 for the numerical uncertainty estimation. Also, considering the random uncertainty in the experimental BOS measurement, we will propose a framework to combine the random uncertainty with the estimated numerical uncertainty to obtain the total uncertainty of the density field. These adaptations will be discussed in more details in the following slides. The adaptations and the numerical uncertainty estimation method was tested on a synthetic density field described as follows using a sinusoidal function, where lambda is the length scale of the sinusoidal field. To determine the order of accuracy of the numerical integration, several approaches can be used. First, the formal order of the numerical scheme can be employed as an estimation, although in some cases the formal order can be different from the order of accuracy. Second, the order of accuracy can be observed by the rate of change of error with grid refinement, and at least the results from 2 grid spacing levels are required. Also, the order of accuracy can be observed by the rate of change in the difference between solutions at different grid spacing levels, and this observation requires 3 levels of grid refinement. The 2 observation methods require that the solutions from different grids are within the asymptotically convergent range and smooth. Considering the experimental BOS measurement, the error-based observation cannot be performed because of lack of ground truth to assess the errors. The residual-based observation is not feasible as it requires 3 grid resolution levels, and the downsampled BOS measurement may not satisfy the requirement to be smooth. Considering the fact that the partial differential equation solved for the integration is elliptical, and the previous analysis only suggested that the formal order fails with hyperbolic solutions. Therefore, we propose to use the formal order as the order of accuracy for the numerical uncertainty estimation. The order of accuracy estimated and observed from the synthetic fields with different length scales were obtained and compared here. The results suggested that the formal order matched the error-based observed order of accuracy. The residual-based order estimation fails due to the subsampling process, which created insufficiently resolved fields as previously discussed. So it is appropriate to use the formal order as the order of accuracy. To decide the factor of safety for the numerical uncertainty estimation, we compared the standard numerical uncertainty defined as the standard deviation of the bias error with the numerical uncertainty estimated with a factor of safety of 1 for the synthetic fields with different length scales. Good agreement was found between the results. Therefore, we propose to use a factor of safety of 1 to estimate the standard numerical uncertainty for BOS, instead of using an empirically chosen value to indicate a 95% confidence interval as in the literature. To combine the numerical uncertainty with the random uncertainty from the previous UQ analysis, we assume that the numerical error is uncorrelated with the random error. Therefore, we can combine the standard random uncertainty with the standard numerical uncertainty using the presented equation. We have applied the uncertainty estimation to synthetic density fields with different noise levels, and the predicted total uncertainty matched well with the total error in terms of the RMS values as suggested by the histograms. In addition, we have applied the numerical uncertainty estimation to the synthetic BOS images rendered using a retracing-based image generation methodology based on a predefined sinusoidal density field. The rendered images were processed using Prana with a standard cross-correlation procedure for 2 passes in an iterative window deformation framework. Here are examples of the density field and the displacement fields from cross-correlation with different window sizes and leading to different spatial resolutions. The error analysis below suggested that the obtained numerical uncertainty underpredicted the bias error in the density field for both spatial resolutions. Further analysis suggested that the discrepancy between the numerical uncertainty and the bias error in the density field was due to the additional error introduced upstream of the density gradient integration step of the BOS measurement. Here we are showing the error in the density gradient estimation from the light ray displacement as well as the cross-correlation displacement. And these errors were caused by the optical model used to estimate the density gradient from the displacement field expressed by the equation here, which was a linear approximation of the nonlinear ray trajectory through the density gradients. This error source was a known factor and caused more significant bias error in the density field compared to the numerical error from the integration. In summary, we have proposed a framework to estimate the numerical uncertainty for BOS density integration using Richardson extrapolation. We also combined the numerical uncertainty with the random uncertainty from previous study to provide a total uncertainty of the BOS density measurement. The method was validated with synthetic fields and applied to synthetic BOS images. It was also found that the numerical uncertainty may not be the dominant factor for the systematic error in the BOS density as compared to the errors caused by the optical model used to estimate the density gradients. The future work includes applying the numerical uncertainty estimation to experimental BOS images and developing uncertainty quantification method for the systematic error due to the optical model. Thank you.